Welcome to lecture B15. The main point of this lecture will be the normal distribution, but I want to start with another example of the hypergeometric distribution. This example is more general than the previous examples we've worked, and I think by looking at this more general example, you may get a better understanding of exactly how the hypergeometric distribution works, and also a better appreciation for how powerful it can be for some problems. So let's look at the following example problem. Let's suppose that there are 4 red balls, 5 white balls, and 6 blue balls in a bucket, and that 6 balls are drawn from the bucket at random and without replacement. What is the probability that these 6 balls will consist of 3 red balls, 2 white balls, and 1 blue ball? Well, if you will stop the video for a moment and think about this problem, I think you'll quickly come to the conclusion that unless you use your knowledge of the hypergeometric distribution, this is a very difficult problem indeed. I think it would take you quite a long time to try to solve this without using the hypergeometric distribution. However, with the hypergeometric distribution, it requires essentially no work at all. You just write down the answer immediately, and it's very easy. So let's see how that goes. Okay, the probability that we're looking for is a fraction, just as always with the hypergeometric distribution, and let's start with the denominator. Now, why do we have 15 choose 6 here in the denominator? Well, the reason is simple. We have a total of 15 balls, 4 red, 5 white, and 6 blue. 4 plus 5 is 9, plus 6 is 15. So we have a total of 15 balls, but we're choosing 6 of those. So altogether, there are 15 choose 6 ways in which we could choose 6 balls without replacement from 15 balls. That's all the ways in which we could choose 6 balls, again, from 15 without replacement. But of course, we're not interested in all of those ways. We're only interested in the ways that would give us 3 red balls, 2 white balls, and 1 blue ball. So how many ways of picking 6 from 15 would yield exactly those results? Well, let's just look at each one separately. And how many ways can you pick 3 red balls from 4 red balls? 4 choose 3. And now notice 4 choose 3 is just 4, and that makes perfectly good sense that there's 4 ways in which you could choose 3 red balls from 4 red balls, because you can think of it, if you're choosing 3 out of 4, there's the same thing as choosing which one to leave behind. And you could leave behind the first red ball, or the second red ball, or the third red ball, or the fourth red ball. So that's how there are 4 ways in which you can choose 3 red balls from 4 red balls. Likewise, and how many ways could we choose 2 white balls from 5 white balls? 5 choose 2. And in how many ways could we choose 1 blue ball from 6 blue balls? 6 choose 1. And so if we multiply those together in the top and divide by 15 choose 6, we have our answer. Just that simply. And there's one other thing I'd like to point out. I don't believe I pointed this out before, but it is a good thing to notice with the hypergeometric distribution, and that it is that when you have a hypergeometric distribution, the numbers in the top for the numerator add up to the number in the top for the denominator. 4 plus 5 is 9, plus 6 is 15. And likewise, the numbers in the bottom in the numerator, 3 and 2 and 1, will add up to the number in the bottom of the denominator. 3 plus 2 plus 1 is 6. So we see, again, that this problem that is very difficult to handle by other methods is very simple when you use the hypergeometric distribution. So I hope that that helps you to understand it better, and be sure that you're comfortable and familiar with this example. Now we move on to the normal distribution, which is a distribution for continuous random variables. and is very widely used. It appears in many applications. I'll leave it to you to read through the section and look at the exact expression for the density and other discussion there, but I want to, as usual, do some problems with you. And so we'll jump right into this and first look at problem 24.8.2. Now, if we're going to do problems with the normal distribution, we're going to be using these tables that we discussed before, and let me just remind you of these. Of the four tables that we discussed already, the two were about the normal distribution, and those were tables A7, given here, and table A8. And notice that in both 7 and 8, you see this symbol phi appearing. Here it is again, phi. Phi is referred to as the standardized normal distribution. And the way that it is related to something we already know is given right here in this equation. Here, capital F, as usual, is the distribution function or cumulative distribution function. And the way that the standardized normal distribution, phi, is related to the cumulative distribution function, capital F, is given by this equation. So if you'll keep in mind this equation, it will help you when you try to use tables A7 and A8 to solve problems with the normal distribution. Now, for this problem 24.8.2, it says let x be normal with mean 105 and variance 25. Find A, the probability that x is less than or equal to 112.5, B, the probability that x is greater than 100, and C, the probability that 110.5 is less than x is less than or equal to 111.25. So let's start with problem A. The probability that x is less than or equal to 112.5, we recognize that that is exactly equal to capital F of 112.5, because that's the way that capital F is defined. It is capital F of little x is the probability that the random variable is less than or equal to little x. So this is just using the definition of capital F. And now, in getting from this part to here, we use the definition of phi. So capital F of 112.5 is little phi of 112.5 minus mu, which is, we're given that the mean is 105. So for this mu here, we stick in 105. And over sigma, now what is sigma? Well, the variance is 25. And remember, the variance is sigma squared, so sigma is the square root of the variance, or 5. So that's how we get this 5 in the denominator. And then this is phi of 7.5 divided by 5, or phi of 1.5. And now if we look at the tables, this is really quite simple. This first problem, you see that you have, in the first column, you have z's, in the second column, phis of z's. Third column, more z's and more phis of z's, and so on. So we just need to find out in which z column 1.5 appears, and it's over here in the third z column, right down here at the bottom. And we have 9332 for phi of z, and let's check. At the top of that column, we have the 0 point, so this should be 0.9332. 0.9332. So 0.9332. That is the probability for this x that it is, we'll assume a value that is less than or equal to 112.5. So that's very simple. Now let's look at problem B. What is the probability that the x will be greater than 100? Well, the probability, now I hope that you'll stop this video, think about it for a moment, and then see if you can solve this on your own, and then come back and check. The probability that x is greater than 100 is 1 minus the probability that x is less than or equal to 100, which is 1 minus capital F of 100, which is 1 minus phi of 100 minus 105 over 5, which is 1 minus phi of -1. Now, what is phi of -1? Well, let's look back at the table. And at first, it looks like we have a problem here because no negative values of z are given. Only positive values of z are given. So how are we going to figure out the value of phi of -1? Well, the answer is right here. Up at the top of this table, you see this equation that says phi of -z is 1 minus phi of positive z. So phi of -1 is 1 minus phi of +1. So let's come back over here. And for phi of -1, we're going to substitute 1 minus phi of +1. And so now this will be 1 minus 1 plus phi of 1. When I multiply out this negative sign, distribute it over the interior of the parentheses. And the 1 minus 1 becomes 0, of course. And then we'll just get phi of 1. And now we can look at the table again. And 1 appears in the second z column. And we have 0.8413. 0.8413. So that's the probability that the random variable will assume a value greater than 100. And now finally, C. For C, we wanted the probability that 110.5 is less than x is less than or equal to 111.25. And I very strongly encourage you, you should be able to do this last problem. So stop the video and try this yourself, and then come back and compare with what we do here in the lecture. Okay, well, this is simply equal to capital F of 111.25 minus capital F of 110.5, which will be phi of 111.25 minus 105 over 5 minus phi of 110.5 minus 105 over 5. And so this will be phi. In the first case, we will have 6.25 over 5. So phi of 6.25 over 5. And then we subtract from that phi of 5.5 over 5. And so this is the same thing as phi of 1.25 minus phi of 1.1. And now once again we refer to the table A7. Okay, we had 1.25 and 1.1. So 1.25, the corresponding fee is 0.8944. 0.8944. And for fee of 1.1, we have 0.8643. 0.8643, and so the answer is 0.0301 for C. And that's it for this problem. So once you know how to use these tables, and keep in mind this definition of how phi is related to capital F, this problem is really very straightforward. So now let's look at another example. This will be problem 24.8.4. And this one says the following: let X be normal with mean 3.6 and variance 0.01. Find C such that in the first case we want probability that X is less than C is equal to 5%. The second case, we want the probability that X is greater than C is equal to 1%. And finally, the third problem within this problem is I'm sorry, I've gotten some information for. I looked at the wrong problem. Part 1 of this one should be 50%, not 5%, but 50%. And the second one, and this should be less than or equal to C. Okay. And the second one should be P that X is greater than C is 10%, not 1%. And then finally for part 3, part 3 is we want to find C such that the probability that minus C is less than X minus 3.6 is less than or equal to C equals 99.9%. What I had done before was I had copied part of the problem from 24.8.3 and part from 24.8.4, but now I believe I have this all correct. Okay, so here's what we want to do for this problem, and let's try to figure out how we might go about doing this. Let's look at part 1 first. Now, we want the probability that X is less than or equal to C to be 50%. So, one thing you might think then is, okay, the probability that X is less than or equal to C, well, that's capital F of C. And of course, remember now that this probability here in problem, the first part of the problem is 50%. So that's capital F of C, which is phi of C minus mu over sigma. And in this case, that would be C minus 3.6. And remember now, sigma squared is 0.01, so sigma is 0.1. So we have phi of C minus 3.6 over 0.1. Let's summarize it down here. Phi of C minus 3.6 over 0.1 is equal to 50%. Now let's see if we can find a C that will satisfy that. Well, if we go to the tables and we're looking for a phi that's equal to 0.5, we notice that there is no phi. Now, first of all, we're going to look at table A7. So if we look in table A7 and look for a phi of 0.5, it seems that all the values of phi are greater than 0.5. So let's look then maybe over here at table A8. Now this one it has a different format. Rather than giving given a z, you find the phi. This is given a phi, you find the z. So we have the percentage here. Let's look at 50%, and 50% is right here. And so what z goes with 50%? You see, this is the percentage, is 50%, and what z goes with that? 0. So if we come back here, we get that since phi of this quantity in the parentheses is 50%, then according to table A8, the quantity in parentheses must be 0. So C minus 3.6 over 0.1 is equal to 0. And so C equals 3.6. And actually, this is definitely correct. And in fact, if you're somewhat familiar with the normal distribution already, you might have known the answer already, because you see the mean value of this normal distribution is 3.6, which means that half the time the random variable will have a value less than 3.6, and half the time it will have a value greater than 3.6. So, in other words, the probability that x will be less than or equal to 3.6 is 50%, and therefore that's why C turns out to be exactly equal to the mean here in this first problem, where the probability given is 50%. Now, before we move on to the second part, let me make one more comment. You actually could have used table A7 to find the answer there, even though the table doesn't list any value for phi that is exactly equal to 0.5. Now, how would you do that? Well, you need to come back up again to this equation which we've used already. Let's see, this equation says phi of negative z is equal to 1 minus phi of z. Well, you see, this table starts with z equals 0.01, but what about phi of 0? Well, let's use this equation. Well, let's come back over here. Phi of negative z is 1 minus phi of z. So this will be just a side note. So phi of negative z equals 1 minus phi of z. And if we try z equals 0, what does this tell us? Well, negative 0 is 0. And so we would get phi of 0 is 1 minus phi of 0, or 2 phi of 0 is 1, or phi of 0 is 0.5. And so, and of course, that's the information that we got from table A8 that allowed us to solve this problem. But I'm just showing that if you had used this equation from table A7, you could have also found out that the value of the argument that will make phi equal to 0.5 is exactly 0, as we found from and used right here. So whichever way you want to solve this problem, it's more direct to use table A8, but you could have used table A7 as well. So now that you've seen that, I hope that you can get the second part of this problem. Now the third part might be a little tricky, but try to do the second part at least, and then let's come back and look at it together. Okay, the second part of this problem in the second part, we want to calculate the probability that x is greater than c. We want that probability. We want to find the value of c that will make that equal to 10%. Well, the probability that x is greater than c, now once again, if you, one way we can approach this, if we look at table A7, all these probabilities we have here, all the values for phi, which is related to f, which is related to probability, all of these are greater than 1/2. So it looks like table A7 would not be the way to go. What about table A8? Well, there indeed we have 10%. So this looks like, yes, this would be more useful in this case. So what value of z will make phi equal to 10%? Well, the answer is minus 1.282. So let's see how that will, if that will help us do this problem. Well, let's see here. We'll have, let's see. I guess the way I would approach this is the following. I would say the probability that x is greater than c is 1 minus the probability that x is less than or equal to c. And of course, once we've written it in that way, then we know that that is capital F of C. And now if we do just a little bit of algebra, of course, we now need to write this 10% as 0.1. And so we have F of C is 0.9. And so phi of C minus mu over sigma is equal to 0.9. And mu is 3.6, and the variance is sigma is 0.1, so we have phi of C minus 3.6 over 0.1 is equal to 0.9. And now we can use a table let's look here. We have actually phi is 0.9 or 90%, so actually we'll go over here to this last set, and for 90% we see the z that makes phi equal to 90% is 1.282. So we have c minus 3.6 over 0.1 is 1.282. Yes, 1.282. And so c minus 3.6 is 0.1282, and therefore c is 3.7282. And that's how we would solve that problem. So you need to translate first from the probability to the capital F function, and then use the capital F function, also, called the distribution function or cumulative distribution function. And then once you have the capital F, then you get phi. And once you have phi, you can use tables either A7 or A8. And I believe in this case, let's see, phi was equal to 90%. So it's very convenient, as we saw, very convenient to use table A8. Now, what if you had tried to use A7? If you can find an entry here where phi is exactly equal to 90%, and see, the problem is that we don't get one exactly. We have here 0.9015 or here 0.8997, and you can see, remember, the answer we came up with is 1.282. Here we have 1.28 and 1.29. So as we would expect, it's somewhere in between those two, but we don't find, unless we do some kind of interpolation here, we could not find exactly to 3 decimal places what z is equal to. But by using table A7. But if we use table A8 and look up here for 90%, then the z that will make that, that will give you that phi, is 1.282. So in this case, it's both easier and more appropriate, more accurate to use table A8. Now, what about the third part of this problem? Here it says the probability that negative c is less than x minus 3.6 is less than or equal to positive c equals 99.9%. Well, as we've noted before, this form is the same as saying, well, actually, let me note something for you here. When we have exactly this form, this is actually something a little bit new for us, and it exactly matches a form here in table A8, where you have d of z is equal to phi of z minus phi of minus c. We can see we're going to use something along these lines. Now, let's, first of all, though, we need to do our usual conversion from probabilities, because here we have probabilities, and we want to convert that to phis. And remember, first we will write it in terms of capital F, and then we'll go from F to phi. So this is the same as saying capital F. Well, okay, let's maybe do it like this. The probability that negative c is less than x minus 3.6 is less than or equal to c is the same thing as the probability that negative c plus 3.6 is less than x is less than or equal to C plus 3.6. And now that we have this in terms of x rather than in terms of x minus 3.6, we can make the observation that this is equal to capital F of C plus 3.6 minus capital F of minus C plus 3.6. And remember, on the right-hand side, that's equal to 99.9%. Now again, remember, I'll just put a reminder over here on the right-hand side. Remember that capital F of little x is phi of x minus mu over sigma. And in this problem, mu is 3.6 and sigma is 0.1. So if we now return to this equation and use this relationship between capital F and phi, then we will get capital phi of, and we need to, for x, we need to substitute C plus 3.6. So capital phi of C plus 3.6 minus mu, but mu is 3.6, so minus 3.6 over 0.1 minus phi of C, let's see, we'll have minus C plus 3.6 in the second case here, minus C plus 3.6 minus mu, so minus 3.6 over sigma equals 99.9%. Well, fortunately, this simplifies quite a bit. We will have a phi of 10C minus phi of negative 10C is equal to 99.9%. And now that we have this in terms of the phis, then as we said a moment ago, we come back over here to the tables and notice that phi of something minus phi of the negative of that something, phi of z minus phi of negative z, is exactly this function d of z. So we can come back over here then and say that this phi of 10c minus phi of negative 10c is the same thing as capital D of 10c. And that's equal to 99.9%. And now go back to table A8. And for the we look up 99.9%, and that's here. We see in the percentage columns, we come to the, not the first percentage column or the second percentage, or the third percentage column. We come down here to 99.9, and the value of z that would make d equal to that. See, this is the value of z, excuse me. This is the z of phi column. So that means that this is the value of z that would make phi equal to 99.9%. And this other column to the right of that is z of d. So this 3.291 is the value that z would need to be to make d equal to 99.9%. So we have z, we have that the argument is 3.291. So 10c is equal to 3.291, and therefore c is 0.3291, just like that. So that's the way that you would solve that problem. But keep in mind that in all three of these, we first take the probability that is given, convert that, find out what that tells us about capital F, and you see here again, and then here again, and then once we have the problem in terms of capital F, we convert to phi, and once we have it in terms of phi, then we can go ahead and use one of the tables to solve the problem. Notice we did the same thing here in this previous problem. We go from probability to capital F to phi. Probability, capital F, phi, probability, capital F, and then phi. So that's the procedure that you will want to follow in solving these problems with a normal distribution. So now let's look at some problems for lecture B15. Both of these problems are very similar to problems in the book. The first one, B15-1, is very similar to problem 24.8.5. It says, if the lifetime X of a certain kind of battery is normally distributed with mean 5 years and standard deviation 1 year, now keep in mind that's the standard deviation, that is sigma, that is not the variance. Okay, so the mean is 5 years and the standard deviation is 1 year. And the manufacturer wishes to guarantee the battery for 4 years. What percentage of the batteries will he have to replace under the guarantee? And the answers are A, 84.13%, B, 11.19%, C, 78.81%, and D, 15.87%. And then for problem B15-2, which is very similar to problem 24.8.11, it says, if sick leave time X used by employees of a company in 1 month is normal with mean 1,000 hours and standard deviation 100 hours, how much time T should be budgeted for sick leave during the next month if T is to be exceeded with probability of only 20%? And the answers here are A, 915.8 hours, B, 1,084.2 hours, C, 579.3 hours, or D, 788.1 hours. And then, as usual, we'll have at least one more problem in class. So that's it for lecture B15, and good luck.